Welcome to the new series of lectures based upon organic chemistry. So, in this lecture, we will discuss organic photochemistry. Organic photochemistry is a very important topic as far as CSIR, UGC, NET and GATE. So, from the very basic things, I will explain each and everything regarding the photochemistry. So just watch it with patience. Very slowly you will get each and everything, and you can become able to solve each and every problem related to organic photochemistry and CSIR NET or GATE exam. So let's start it. Suppose we have a reactant R is changed into P. So R is your reactant, P is your product. When this R change into P by striking a light, when you strike a light of some suitable frequency, your reactant then change into product. So such type of reactions are called photochemical reactions. Photochemical means, photo means light. The light, the reaction which take place in the presence of light. So you took a reactant R, strike a light of suitable frequency, and that reactant change into product. No doubt this will not take place in a single step. There are many steps, and for each step, what is the mechanism we will understand one by one. So how will you compare it with some simple chemical reaction? Suppose we have a R and it's going to change to P. If we add some reagent here, R, some reagent, that will give you P. So this is your organic chemical reaction. Organic chemical reaction. For example, we have a ethene. Adding Br2 in the presence of CCl4, you will get 1,2-dibromoethane. So ethene is your reactant. Bromine in the presence of CCl4, that is your reagent. Like Br2 is the reagent, CCl4 is a solvent. Okay. Now in this reaction we have a reagent, but in photochemical reaction, this light which we are using, that act like a reagent. It means your light is act like a reagent. Okay, so that's the difference between these two types of reactions. In a simple chemical reaction, we have a reactant and we added some reagent to it and it changes to product. But in case of photochemical reaction, we have a reactant, we just radiate with some suitable frequency wavelength. Generally, we use 310 nanometer or that 500 picometer that we will discuss later on in this lecture. That changes to reactant, changes to product. That is a photochemical reaction. So in photochemical reaction, we can say that our light is act as a reagent. Now, this R, now we are going to expand this reaction. This reactant is in ground state. Okay. So when you strike a light, it go to excited state. We can write it R star. So this is excited state. Star represent excited state. That is the stable, high energy. Okay, and this excited state then change to product. So this is your reactant R, that is in the ground state. When you radiate it, go to an excited state, that is represented as R star. And then R star, because it is unstable, it immediately go to change into product P. Okay, let's expand it more. Now we have a reactant R that is in the ground state. Okay, so it changes to R star, that is in the excited state. Now before it convert to product, it immediately gives an intermediate. Okay, this R star is not directly changed to P. It first converted into some intermediate. So I will write it I. So what is I? I is your intermediate. Intermediate. Okay, and this intermediate is in ground state. Is in ground state. Then this intermediate, because it is highly reactive, it changes to product. So this intermediate, that may be carbene, that may be nitrene, this intermediate that is formed from this R star, that may be this I may be carbene, that may be nitrene, or that may be diradical. Okay, because these carbene, nitrines and diradical, these are highly reactive species, so they immediately change into product. So what are the possible reactions that may take place when the R changes to R star? This R star is in excited state. It may undergo some electron transfer. It may undergo electron transfer. It may undergo atom transfer. Or it may undergo some bond breaking. Or it may undergo some bond breaking. So when our reactant R that changes to R star by observing some suitable frequency in excited state, this excited state species that may undergo electron transfer, that may undergo atom transfer, or some maybe there's some breakage of bond, or maybe there's some making of new bond. By doing any one of these, this R star that changes to intermediate. Okay, and this intermediate is in a ground state. Keep in mind, this intermediate is in a ground state. An intermediate may be carbene, it may be nitrene, or it may be diradical, and these are highly reactive species. And then these intermediates, they changes to product P. So now these are the steps mainly. So first we will understand this step, how the R changes to R star. One by one we will complete this. This part will cover the introductions of organic photochemistry. After that introduction, you will become able to do any reactions related to this photochemistry. So that's why see this introduction very carefully here with patience. Okay. Now how the R changes to R star. We are concentrating on this that R that changes to R star. Or changes to R star. Suppose we are taking an example of some aldehyde. So this is here formaldehyde. Okay. So how many types of transitions are possible when we irradiate this molecule with the light? These electrons are lone pair. Okay. These electrons are non-bonding electrons. Non-bonding electrons, and these are pi electrons. Okay, and this bond is sigma, so these are sigma electrons. So if you draw the energy levels of these, so we can draw like this, that this is these are the levels bonding and various transition. So this is your sigma CO. Sigma CO means the bond between carbon and oxygen, sigma electrons, and this is sigma level. This is pi level of C and O. It represents pi electron. This is its non-bonding, represented as N. This is your pi star, anti-bonding, and this is your sigma star. So these are the energy levels for this simple model molecule formaldehyde. Now, which transitions are possible? Okay, so first transition is maybe N to pi star. That's very common transition in photochemistry. This transition is N to pi star. Second is N to sigma star. Okay. Third is pi to pi star. This is also very common. generally in aromatic or polyaromatic hydrocarbons, pi to pi star transition. Then your pi to sigma star transition. Okay. Next is your sigma to pi star transition. And last is your sigma to sigma star transition. So these 6 transitions are possible. So these 6 transitions are possible. Now, if we give minimum energy to this reactant, using a H nu means a minimum energy. We are giving a minimum energy using a wavelength such that it provides a minimum energy. So, if minimum energy is provided to R, then which transition is possible? Obviously, your N to pi star transition is possible. So when we are using a minimum energy, only N to pi star transition is possible. So we are assuming and we are taking minimum energy, so we will discuss only N to pi star transition. How N to pi star transition take place? So there is a levels, energy levels. Okay, one electron is here, one electron is here. This transition is called N to pi star transition. When we radiate, the electron jumps to. If we think about the spin, then what will be the spin? Now in the ground state, if we have 2 electrons and we radiate with the light, the one electron that jump from N to pi star. This is level N, this is level pi star. So if we just concentrate on the spin, so what will be the possible spin? If one electron is here, when the other electrons go to the excited state, its spin changes. Second possibility is one electron is in the ground state. When one electron go to excited state, spin remain same. So this is called a singlet, and this is called a triplet. So 2 spin states are possible. The question is, why it's called triplet? So let's see, we have 2 electrons, this and this. So this is your applied magnetic field. So this arrow represents the applied magnetic field, direction of applied magnetic field. Okay. So the spin of this is say plus half, spin of this is say plus half. Overall spin become additive, so it become plus 1. Now this plus 1 spin may have 3 orientation in the space. It may be in the same direction as that of the applied field. You can draw it like this. It may be in the same direction as that of the applied field. Then it is called plus 1. It may be in opposite direction than that of the applied field, means in this direction, that is called minus 1. Or third possibility is it may be perpendicular to the direction of the applied field, means in this direction, 0. So we have 3 directions in which that spin may behave in the presence of applied magnetic field. When you apply a magnetic field, the spin may behave in 3 ways, either in the same direction or in the opposite direction or in the perpendicular. So that's why it is called triplet, because it is behaving in a 3 way. So that's why it is called a triplet. Okay. So what is studied here? R changes to R dash. These are the various transitions. And if minimum energy is provided to R, then we get the N to pi star transition, and this is N to pi star transition generally, and this is with respect to spin. We have a 2 state, either singlet state or a triplet state. Next. Now we will compare the energy of singlet and triplet. Okay. So when you draw the diagram, this is S0, that is a spin ground state, and this is your S1, spin singlet. S1 is singlet. 0 means ground, 1 means first excited, S singlet. And we get a T here, that is a T1, that is a triplet. T1 is triplet excited state. Okay. Now, why question is that, why triplet has lower energy than singlet? Why triplet has lower energy? This is ground state. This is the energy gap between ground state and singlet state, and this is the energy gap between ground state and triplet state. So this is lower energy, and in this we have energy. So why triplet has lower energy? Now see, what is singlet? One electron with, you can say, plus half, another electron say minus half. This was the singlet. So when these two electrons, they are present in an opposite spin, so they love to pair up. Okay, so these electrons tends to pair up. The following Bond's rule, is tries to pair up. So when they pair up, okay, when they pair up like this, then there will be repulsion. When they pair up, there will be repulsion. But in case of triplet, it was a singlet. Now we have a triplet. In triplet, both the electrons, they are with the same spin. Okay, they are not eager to pair up. Because they have the same spin, not eager to pair up. That's why there is no repulsion. And if there is no repulsion, it means it's more stable. If it is more stable, it means it is a lower energy. So that's why triplet state has lower energy than the singlet state.